All right, guys, still on page 38 of your notebook, looking at electron dot formulas and using VSEPR. Don't let the word scare you. It stands for valence shell electron pair repulsion theory. We're going to take our two-dimensional electron dot formulas and look at how they're supposed to be in 3 dimensions, okay? All right, so some background information that you need to know. First of all, electron pair geometry is the way the electron pairs are arranged around the central atom. Okay, so looking at, are there lone pairs, are there bonds, wherever the electrons are, that's going to give us our electron pair geometry. The other type of geometry is molecular geometry. This has to do with the atoms. The arrangement of 2 to 4 atoms around a central atom. Okay, that's what we've been doing all along, right? The Lewis dot formulas are the two-dimensional representations of atoms around a central atom. And therefore, they are not complete representations of the molecular structure of the compounds. However, they are critical to discovering the 3-dimensional structure of compounds, as they can be used to predict bond angles. That's going to be the key here. That's what we're trying to do. We're trying to look at these angles that exist when you start putting the atoms together, okay? So the correct structural and molecular formulas of compounds can be determined by this method. So then, how do the electron dot formulas predict the bond angles? Well, we have to remember that electrons carry a negative charge and that like charges repel. So if I have a pair of electrons here and a pair of electrons here, they're going to repel each other as far away as possible. So using that idea, we look at the electron pairs shown in the electron dot formula actually are going to repel each other in the real molecule. So the valence shell, electron pair repulsion theory, yes, it's a big old long word, we fondly refer to it as VSEPR. Yes, I know that it's not phonetically pronounced like that, but we call it VSEPR because that's close enough. It states that the valence electrons of a molecule will distribute themselves around the central atom so that they are as far away from each other as possible. Why? Because they repel each other and they like to be as far away from each other as possible. Okay, so in the example shown above, this one up here, the 3 fluorine atoms of BF3 have the same bond angle, and you can see in the picture that it's 120 degrees between them due to the fact that their electrons repel each other equally. Okay, so what does that all mean in terms of what you have to be able to do? Turn the page to 39. Okay, so on page 39, this is kind of the meat of the lesson. This is what you need to take away. So the true distribution of electrons around the central atom is known as electron pair geometry. That means that these electrons can either be shared, found in the actual covalent bond, or lone pairs on the central atom. So we're looking at bonded electrons and lone pairs of electrons. So the electron dot formulas of covalent compounds are then used to predict the molecular structures. Okay, so this table is what you need to focus on. When we draw our Lewis structure, we look at the total number of electron pairs around the central atom. If you have 2 lone pairs of electrons and you have 2 bonded atoms, then we end up with the geometry called linear. If you have 3 electron pairs around the central atom and 3 of them are bonded, then we have trigonal planar. Okay? and then so on and so forth. And okay, and the best way to do this is just start looking at some examples. Okay, so in this table below, we need to draw the electron dot formula of each compound. Then we're going to use this table up here to predict bond angles and molecular geometry. Remember that the total number of electron pairs, this one right here, refers to the electrons surrounding the central atom. Also, the number of bonded atoms refers to the atoms bonded again to the central atom. Okay, so let's go ahead and start off BEF2. All right, so I'm going to get a count. I'm going to do that over off to the side, okay? So BE is in group 2, and there's one of them in our formula, so we get 2 electrons from BE. Fluorine, there are 2 of them in the formula, and since it's in group 17, that gives us 14 electrons. Oops, I just wrote over my formula. Okay, so we take 2 plus 14, and that gives us 16. And that's how many electrons we have to work with, okay? So the next part is actually drawing this, and we're going to put BE in the middle and give it 2 fluorines around it. We've used up 4 of our electrons, and that's going to leave us with 12, okay? 12 electrons to distribute. All right, so then we're going to start off on the fluorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so then BE is actually one of those other exceptions to the octet rule. It's perfectly happy just being bonded twice. There's no need for extra sharing of those electrons. Okay, so total number of electron pairs, we have 2 because there's an electron pair here and an electron pair here. Now, how many bonded atoms? Again, we have 2. So then the molecular geometry for 2 and 2 is linear. And the bond angle that gives us is 180 degrees. Okay, so it's the same Lewis structures that we've been drawing, but all we're doing is analyzing it using the table that's given. Okay, let's try another one. BF3. Boron is in group 13. There's 1 of them, and it has 3 valence electrons. That gives 3. Fluorine, again, is in group 17. But since there's 3 of them, I multiply by 3. That gives me a total of 24 electrons to work with. B goes in the middle, and 3 fluorines surround it. Okay, simply by bonding, I have used up 2, 4, 6. That gives me 18 electrons to distribute. Yet again, we have another violation of the octet rule belonging to boron. Put that in the memory bank, okay? BE and B, beryllium and boron, violate octet rule. Okay, so add that to your bank of understanding for violations of octet rule. So we've used up all of our electrons. How many electrons are surrounding the central atom? We have 2, 4, 6. So, I'm sorry, how many pairs of bonded atoms? We have 1, 2, 3. So we have 3 total pairs of electrons, and we have 3 total bonded atoms. So we put 3 and 3. This gives us a trigonal planar arrangement, and each of the bond angles is 120. Okay, SO2. S is in group 16, so it has 6 valence electrons. Oxygen is also in group 16, but we're going to multiply that 2 since there's 2 of them in the formula. We have 18 electrons to work with. Okay, so we have sulfur in the middle, oxygen on either side, and I'm just going to switch colors right now because I don't want these electrons to bleed together. Okay, so that used up 4 of my electrons. So I'm going to subtract that out, which gives me 14 to work with. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That last pair of electrons, remember, needs to go over to the sulfur. Now in SO2, there should be a double bond. This is actually going to lead to some resonance between the right side oxygen and the left side oxygen. Remember, in resonance structures, there's more than one possible structure. There's no need to worry about that right now. Ultimately, what you're going to have is sulfur with one double bonded oxygen, and it could also be on the other side. Okay, but that's not going to affect anything about the valence shell electron pair repulsion theory. You're still just going to address it the same. Now, this one has 3 areas of electron density. It's got 1 bond, 2 bonds, and a lone pair. So that's 3 electron pairs. Of those 3 electron pairs, only 1, 2 are bonded. So total number of electron pairs was 3, and the number of bonded atoms is 2. So that's going to give me this one right here. And that molecular geometry is called bent. Okay, and that's going to give 119.5 degrees bond angle. Okay, go ahead and try those last 3 on your own. And as usual, if you have any questions, please be sure to ask.